Hello and welcome to Lecture 2 of Circuits in Phys 1201. This lecture is going to be all about the simplest sort of circuits, which are circuits that contain nothing but resistors and batteries. The next few lectures are really about something called circuit analysis, so I should explain what that means. So suppose we have some circuit and we know a bunch of things about it. And so in a common case, maybe this is a circuit someone's already put together and some things are just printed on the circuit elements. So for example, on batteries, most batteries will tell you what the voltage across the terminals is. That's what we call the EMF, which we represent by epsilon. The resistors have these colored strips, and those are a code that allow you to read off the resistances R of the resistors. And capacitors often have their capacitances, C, written right on them. Or another case might be that instead of working with a circuit someone has already put together, you're designing a circuit. And maybe you know there's some device, maybe a motor in the circuit somewhere, and you know that it needs a specific voltage applied across it, or maybe a specific current provided to it. And so those are now things you know about this circuit. Let's go to this simple case, though, of an all-resistor circuit. So it's just got a battery and some resistors. And let's say we know the EMF of the battery because it's printed right on it, and the resistors of the resistances because we can read the codes. And we want to know everything about the circuit. And so what that means is, at the moment, we don't know the currents through the resistors. And we know the voltage across the battery, that's what this epsilon means, but we don't know the voltages across any of the resistors. So those are our unknowns. And what we mean by circuit analysis is just the process that takes you from the knowns to the unknowns. And that looks like an awfully long list of unknowns, but something to recognize here is that for resistors you have Ohm's law, which is a relationship between the current through the resistor and the voltage across it. And so at the point that you know all these currents, you can then easily determine all the voltages. The other thing I haven't mentioned is power, and often that's actually really what you want to know because it'll tell you things like how long a given battery will run the circuit. But again, once you know all the currents, you know all the resistances, you can easily calculate all the powers. There are some special cases that'll help us simplify the job of circuit analysis, and so we're going to start with them. So here's one of the simplest circuits we can draw. It has two resistors in series. And we already know how things work in series. While I've written I1, I2, we know for things in series, whatever current goes through this all has to proceed to flow through this. And so all three of these currents are the same. And we're now going to use that to figure out a way to simplify this circuit. So think about how Kirchhoff's loop law will play out. If we think of walking around this loop, we can now write down the voltages. We walk up a voltage epsilon as we step through the battery. As we step through the resistor, the voltage drops. We're going with the current, and these charges are losing electrical potential energy as they go through the resistor. So there is a drop in potential, and it is I R1. It is I1 R1, but I1 is I. And so this, what I've just written here, that's delta V1. It's just a different way of writing it. And similarly, as I go through this next resistor, there will be another voltage drop, like so. And Kirchhoff's loop law says that those all add up to 0 because we have to get back to the potential that we started at. And so if you just solve that for epsilon, it looks like this. And I can rewrite that like this. So what? Why would I rewrite it this way? Well, look, this is a resistance. That sum of resistances is a resistance that I could call Req. And one way of thinking about what that Req, or equivalent resistance, means is that if you had a different circuit with the same battery and a resistance equal to this Req, then the current running around in this circuit would be the same as the circuit that's the current that's running around in this circuit. And so this resistor is in some sense equivalent to this pair of resistances. And so our Req is just R1 plus R2. And this would work if I had more than two in series. So I'll just write plus dot 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 for as many resistors as you have that are all in series. The other special case is circuit elements in parallel. And so let's try and do the same trick. So here we have two resistors in parallel. And what we know about things in parallel is that the voltages across them are the same. So this must be true. And we want to think about how to simplify it again into a circuit that just has one resistance. And if we do, then whatever current is going through the battery here would be the same current as would go through the battery in this case, and it would be related to the epsilon and that resistance this way. So if we can take all of our Kirchhoff's laws and get something that looks like this, we'll be able to figure out what the equivalent resistance is. So again, I'm going to think about loops, but now I have two loops. So here's loop A, and I can also think about a loop B, and I can write down the loop law for each of them. And they're just going to be that I go up epsilon, and then I come down I1 R1, and that's 0. And in the other loop B, I go up epsilon, and I come down I2 R2. And then the other thing I have to work with is a junction. I can think about this junction, and I can write the junction law there. I have a current I in, and I have currents I1 and I2 going out. And now I can put this all together and arrive at something that looks like this. The way I'm going to do it is that I'm first going to solve for I1 and I2 out of these. So you can quickly verify that these solve to give these expressions for those currents, and I can now plug those in here, and I get that I is, and I can rewrite. And finally, I can solve for epsilon to get something that looks like my target. It's going to be like this. It's a bit of a mess. And so that shows us that our equivalent resistance is this messy thing here, which you can write a little more cleanly this way. And the way you'll often see this written is that 1 over the equivalent resistance is, and now again, this applies to more than two resistors, and so I'll write plus dot dot dot. So here we have a circuit where we know the battery voltage and we know all the resistances. And we would like to know all the currents, because if we find all the currents, we'll be able to find everything else. And so we're going to use this method of progressively reducing this to simpler circuits to do that. And I will say at the outset, I don't like this method. I find it fiddly and annoying. I'll show you the method I like later. But most students seem to prefer this method. So here you go. So we're looking for things we can reduce. And the only pair of resistors that's in a simple relationship here is R3 and R4. They are in series, and so I'll be able to reduce them to an RA. And we might as well do that. RA, the equivalent resistance of these, well, these are in series, so it's just going to be the sum, R3 plus R4, and so that's just 300 ohms. So, having done that reduction, we have a new simpler circuit, like so. Now, RA and R2 are in parallel, and so again, we'll be able to reduce them to something I'll call RB. Now, here's where students tend to fall down, because students have a lot of trouble manipulating this relationship. So 1 over RB is 1 over R2 plus 1 over RA. And students have trouble with all these fractions. So R2, remember, is 200 ohms. So this is 1 over 200 ohms plus 1 over, and RA was 300 ohms. And if you're going to add those, you need a common denominator. So that's going to give us 3 over 600 ohms plus 2 over 600 ohms, or 5 over 600 ohms. And so flipping both sides, RB is just 600 ohms over 5, which is 120 ohms. And so there is our equivalent resistance. At this stage now, having done that simplification, the circuit is now, and those are in series, and so we can combine those into an RC, which is nothing more than R1 plus RB. And so that is, R1 was 180 ohms, and RB we just found was 120 ohms, and so that is 300 ohms. Now, remember what we actually want is the currents through our original circuit, and it might not be clear to you how we're going to get them yet, but here we go. So our fully reduced circuit is just this. And now the loop law tells us that the voltage across this resistor is the same as the voltage across the battery. And so IRC, where I'm calling the current that circulates in this circuit just I, is epsilon. And so this I is just epsilon over RC, so 6 volts over 300 ohms, which is 0.02 amps. Okay, so now you look at what happens climbing back up here. RC breaks into R1 and RB, which are in series. So that same current I flows through each of them, which means we now know I1. I is just I1. And we can now use the fact that we know that that same current goes through RB to find the voltage across RB. So we know that the voltage, I'll call it delta VB, the voltage across RB, is just what we're now calling I1 times RB. And so that is 0.02 amps times RB is 120 ohms. 2.4 volts. Now, that's going to be useful to us because at our next step of reconstructing the circuit, RB is breaking back out into R2 and RA, but those are in parallel. So we now know that this delta VB is delta V2 and delta VB because they are in parallel, or delta VA, sorry, because they are in parallel. So they have the same voltage. So that's going to let us find I2, because now I2 R2 is delta V2, and so I2 is just delta V2 over R2, which is 2.4 volts over R2, which is 200 ohms. And so that's 0.012 amps. And finally, we know that that 0.12 amps is going to work through this junction here, so we can find IA. There's an IA here. And so the junction tells us I1 equals I2 plus IA. And then since RA breaks into R3 and R4 and they are in series, IA is the same as I3 is the same as I4. And so at this point, we know all of the currents. And we're done.